this is just a traditional Calc 1 problem that we've probably seen a million times before. Consider some function. I've got f of x equals something. We're back in our Calc 1 brain, so there's only one variable. It's only f of x. And my function is now in terms of only one variable. The question is, determine if the function is increasing or decreasing at x equals 3. So what this is saying is, if we increase our x just a little bit, how is the y changing? So in our alternate notation, so we've seen f prime being the notation for the derivative. We've also seen this notation dy dx. And this is really good to help it kind of sink into our head. Like this is saying, if you inch forward a little bit in the x direction, how is the y changing? Increasing or decreasing? So all we want to see is the value of the derivative here going to be positive or negative? You get a positive value for the derivative, the function is increasing. You get a negative value for the derivative, the function is decreasing. So I just think back to all of my gateway rules. Take the derivative, that would be negative 2x plus 4. And to see if I'm increasing or decreasing at x equals 3, I just want to see the value of f prime of 3. So because the value of my derivative is negative, I don't care what the number is. Just because it's a negative number, I can say the function is decreasing. So I can say f is decreasing at x equals 3 as f prime of 3. So we had a kind of a small library of different kinds of notation that we can use to show the derivative. So this notation here, this d over dx, was the derivative operator. That's saying take the derivative of, and we can use different kinds of notation. I can say the derivative of f is f apostrophe or f prime, we would read that. If you want to take the derivative of y, you could call that y prime, that's acceptable. You could use this notation, the derivative of y is also dy dx. So far, all of these mean the same thing, just different kinds of derivatives. Or, excuse me, different ways of writing. And then this is one that we don't typically use, but physics uses, so it's worth putting up here. And then for the second derivative, so I'll call this first derivative. If you take the derivative of the derivative, we can write that as f double prime. And the only one kind of worth mentioning here is if you take the derivative of dy dx, then that special notation there is we write like d squared over dx squared. So again, for the second derivative, f double prime is kind of like done. But for this notation here, just remember the square goes over the d in the numerator, goes over the x in the denominator. if we're wondering, like, hey, why is that? You can kind of think of it as multiplication. It's not actually multiplication, it's just showing a repeated operation. We've got the two d's there, so it's take the derivative twice. In the denominator, probably thinking, shouldn't it kind of be all of dx? In our notation, we just get kind of lazy and don't write the parentheses there. Technically, it should be kind of all of that to the second power. Yes. And then the last thing I want to review from Calc 1, one of our derivative rules specifically that's going to come up is the chain rule.
Good old chain rule.
So just to remind ourselves, chain rule says take the derivative of the outside function, keep the inside function the same, then multiply by the derivative of the inside. So the derivative of sine of something is cosine of something, meaning keep the inside the same, times, yep, derivative of the inside. Here?
Yeah.
I know what you're
Yeah, like I saw that one and like I understand it, but like kind of I just want to see.
If you want the derivative of sine to the third of x, well, sine to the third means all of sine of x. So you got to chain rule that. Drag the power down, subtract 1 from the power. Keep the inside the same times the derivative of the inside.
Okay, that's what I thought, but like I saw
Next one, the only thing here is if I see e to the x over 3, what's another way of writing x over 3? In such a way that I'm ready to take a derivative, I should say. Yeah. How can I rewrite x over 3?
Oh, 1 over 3, yeah.
Yeah, it's 1/3 x. So I'm going to write this line again just for emphasis. So that's e to the 1/3 x plus 6 times 2x plus 3 to the 4th. Derivative of e to the anything is e to the anything times the derivative of the anything. And then I do have a chain rule here. I can drag the power down, subtract 1 from the power, keep the inside the same, times derivative of the inside.
Should we want to simplify it as much as we can?
Say it's multiple choice, and this is our answer, but it's not an answer choice. We should be able to recognize how to get it to an answer choice. If it's free response, I'm not saying, oh, you didn't simplify. It's just you should be able to recognize how to get to answer choices.
Question.
Yeah.
That 1/3 x, you bring down 1/3, and then is it 1/3 minus -1 after you bring it down, or?
No, so the derivative of e to the something is e to the something times the derivative of the exponent.
Okay.
So if I have e to the 1/3 x, this shortcut tells me it's going to be the derivative of the exponent, which is 1/3, times e to the original.
Okay. Got you. Damn easy.
All right. Do we have any questions that we need a refresher on from Calc 1 before we just extend this to Calc 3?
Ew.
Yep.
So are we gonna be doing any like equations with formula and stuff? Okay, so that one you just need the derivative and like a point and the point in that derivative or something like that?
Yes, that's right. But who can guess? In Calc 3, we don't have tangent lines. What do we have? If I had a surface, yeah, you don't have a tangent line, you have a tangent plane. So that'll be our next lesson.
Tangent plane.
But first, we need to talk about derivatives in Calc 3.
Yay. I'm overjoyed.
Motivate this. This says consider the function. So now I instantly recognize I got to get my Calc 3 brain. This is now a multivariable function. This is now f that takes on an x and a y. So looking at my actual equation over here, I've got something in terms of both x and y. So it says consider this function, this surface, with this equation at a given point. So I'm going to go ahead and graph this on Desmos so we know what we're even looking at in the first place. So I have my surface here, f of x comma y. And I want to consider the point 2 comma negative 1. Don't forget, in 3D, that's not actually a point that only lives in the xy plane. How can I get that point to now live on the surface itself?
Surface.
You can find the z. You can either just take 2 seconds, plug in x, plug in y. Don't forget, Desmos is smart enough to know, because I've called this f of x comma y, I can say what is f of 2 comma negative 1. And it can just do the computation for me. So now you can plot the point 2 comma negative 1 comma 4. There it is. And yes, you also could have typed 2 comma negative 1 comma just f of 2 negative 1. Let Desmos do the computation and plot. I'm going to leave it as 4 just so we can clearly see that as a derivative. So in Calc 1, we were looking at curves, we would plot a point, and then like we saw a second ago, we could just ask the question, is the function increasing or decreasing at that point? Now when you have a surface, it's, I don't really know what to say, what to think. Because in Calc 1, it was always as x increases, as we read left to right, in other words, how is the function changing as far as is it increasing or decreasing? But now I've got 2 different variables. So really what we need is a quote-unquote partial derivative. So that's the whole idea of what we're doing in Calc 3. We have quote-unquote partial derivatives. So we saw a second ago the classic question from Calc 1, determine if the function is increasing or decreasing at this given x value. The language for these classic Calc 3 problems look similar but slightly different. So far it reads the same. Determine if this function is increasing or decreasing at that coordinate. If, and now this part's the new part. If y equals -1 and x varies. So the idea is you have to hold one of the variables fixed and let the other variable change. In words, sounds ridiculous. Let's graph it. Let's figure out exactly what that's saying. So it's saying let y equal -1. We remember y equals -1 is a plane. It's going to be a plane that slices through the surface, also passes through our point. Now, we'll notice that we're left with some sort of quote-unquote trace, some sort of intersection. And I've kind of shown that in orange to be super explicit. Let's now just turn off y equals -1. Like turn off the plane. And you're left with, I'll show you the bird's eye view, y equals -1. We see that horizontal line at -1. But now the question becomes, is the function, which don't forget represents the z coordinates, is the function increasing or decreasing? So in other words, is the z coordinate increasing or decreasing when y is -1 but x varies? So y is -1 is this fixed line, but now x is the thing that's changing here. And here's the only thing that we have to let sink into our head. If we inch towards the positive x-axis, which is really helpful why Desmos gives us these giant letters. If I increase in the positive x direction towards this big letter, is the z coordinate increasing or decreasing? Decreasing. So we can say the partial derivative with respect to x, which is now super important. We've always said that in Calc 1, it's like, oh, with respect to x. But now they've got different variables that you can take the derivative with respect to. It's going to be super important. So we know it's decreasing, we know we get a negative number. Let's show kind of algebraically what that looks like. So we're saying let y equal -1 and x varies. So we can use the notation f of x comma -1. This is now a function where the x can be anything. There's your x varies idea. But y is just -1. So I can go ahead and plug this into my original equation up here. This will be 9 minus x squared minus 1. And I want to make sense of all the different lines as we go throughout this. So again, this is saying f of x comma -1. This should now be a function in terms of one single variable, which it is. So x varies. Y is always -1. This shape here, our Algebra 2 knowledge says, oh, well, that's a parabola reflected upside down, shifted up 8 units. And that's what we saw in our trace. I don't know if you guys remember in exam 1, I was constantly asking, like, oh, describe the intersection. And you can see the intersection is a parabola shifted up 8 units, pointing downwards. So if that's true, and we just kind of look at this in the x-z axis, we can say as x increases, then my z-coordinate decreases. So some new notation to show this. If you want to take the derivative with respect to x, we have this notation f sub x. So if you want to annotate that, that is your first quote-unquote partial derivative. And now I'm going to take the derivative, like normal, it's negative 2x. And if I wanted to know what was happening at the point 2 comma negative 1, then now I can plug in x being 2. And I get negative 2 times 2. So I get negative 2. Correct. Yep. So yeah, let's write that down and just kind of think about what does this mean, what does this imply. Now we have our quote-unquote partial derivatives, meaning if I say, is the function increasing or decreasing, it's not enough information. You have to tell me if what changes. This is saying at the point 2 negative 1, this notation tells us if you increase in the x direction, if you head towards the big letter, then you're going to be walking downhill along your surface. So imagine this, I'm always going to describe this like a hike and we're walking. If you're standing at a location of 2 negative 1 in the 2D plane, and you walk in the direction of the positive x-axis, you're going to be walking downhill. Please ask questions. Same function, same surface, same everything. The only thing now is determine if that function is increasing or decreasing if x equals 2 and y works. So visually showing this, it's still the plane x equals 2 intersects with the surface. So to be super explicit, I'm going to draw that trace again. Turning off the plane just to see it better. This is now the intersection. So this is saying hold x fixed. X is not moving. But if x is fixed and now y is allowed to change, how is the z-coordinate increasing? So if I'm standing at the green point and I'm heading towards the positive y-axis, is z increasing or decreasing?
Increasing.
Increasing. So we're starting to really get this idea of a partial derivative of increasing, decreasing. Well, it depends on the direction that you're heading in. It depends on which variable is increasing. So again, on the board, this is just our notation for the function. If we held x being 2, and y is allowed to be anything, then you get a function in terms of only one variable, a function in terms of y. So if you want to show the partial derivative with respect to y, you guessed it, it's f sub y. So, again, this is still just our partial derivative. So just peeking over, looking at the two things that I've got boxed, just kind of really let this sink in. If you travel in the positive x direction while standing at this point, you're going to be walking downhill. Standing at the same exact point, if you just turn 90 degrees and now travel along the positive y-axis, or towards the positive y-axis, you're now walking up. So if we wanted to see both of those quote-unquote bands at the same time, still one location, still one point in space. X equals 2, y equals -1. But if I walk in the direction of the positive x-axis, walk downhill. Walk in the direction of the positive y-axis, walk uphill.
And this all depends on the trace, or is this random trace?
That's a great question. Is your question, does it have to be like,
Parabola for distribution?
oh, no, we're going to have all sorts of services.
So, no, my question is like, if like.
I see, you're asking about the trace itself. The trace doesn't have to be a nice, pretty picture. And we actually don't really care what the shape of the trace is, because we can plug in points and get numbers. It is like you're like 2 seconds ahead of me. That's the nice thing about it. So we were looking at this surface here, and we recognized that when taking the derivative with respect to x, I'll make the second part of C. When taking the partial derivative with respect to x, since a number goes in for the y coordinate, y is fixed, then when you're taking the derivative, you can just treat y like a constant. You know eventually something's going to get plugged in for y. So you guys are going to like this. When you take the derivative with respect to x, take the derivative like normal, Calc 1 knowledge, and anytime you see a y, it's now a constant. It's now a number. The derivative of 9 drops off. The derivative of negative x squared is negative 2x. The derivative of negative y squared, well, hang on, the derivative with respect to x, this to me is now just a constant. Drops off. Boom, done. This is now a function where you input a coordinate and it gives you the partial derivative with respect to x. If you want the partial derivative with respect to y, now, if I'm taking partials with respect to y, x is now a constant. So the derivative of 9 is 0. The derivative of this x term is 0. And I've got the derivative over here as negative 2.
Why do you treat it like a constant?
So, I'm glad I kept this example written up here. So, y varies, and x equals 2. So, anytime there is an x, I know I'm just going to plug a number in for it, a constant in for it. So, when I'm taking the derivative, I know that that's just going to be treated as a constant. Y is going to be the only variable here. You don't seem convinced.
No, I understand, yeah.
All right, let's show some more notation. So just partial derivative notation. So if you're taking the derivative, super important here, with respect to x. We've always just written this in Calc 1, like, oh, yeah, that means taking the derivative. But now this x down here is super important. You're taking the derivative of this function with respect to x. So this is the notation that I just showed a second ago, f sub x. Very similarly, yes, you can now write that as f sub y. If you're taking the derivative with respect to y. And this is really unusual for us because we've always seen like d over dx, d over dt. But now y is a variable that you can take the derivative with respect to. If you want to call it z equals something, similar to in Calc 1, we just sometimes call the function y equals something, then we can call this the partial of z with respect to x. So this is kind of a new symbol for us. This is a script d. It's not a 2, and yes, from time to time you will see me write fast enough that it kind of starts looking like a strict 2. Kind of loops around like that, and it stops there. If you guys are interested, that's called quote unquote del. So you might hear me read that as like del z, del x.
Like DEL or
One more time?
is it like DEL or DEL?
DEL, yep.
DEL.
And is that the same thing as saying, like, take the derivative with respect to
So
x?
take the partial.
This is, yes.
That's
This
the
is
partial.
saying the derivative with respect, the derivative of z with respect to x.
So is it the same as f of x, y?
Yes. Yep.
Okay.
So these are the same thing. Now, over here, I didn't have to show you this notation first, f sub x. There's no such thing as a prominent one or most commonly used one. If this is f of x comma y, absolutely you could have written this as del f over del x. The next one, sometimes we ditch the of x, y notation. This is being super explicit, showing it's a function in terms of x and y. If you just want to mark this, this is kind of like the lazy version. It's saying the same thing as up here, but sometimes we just ditch the of x comma y notation. So in the first couple lessons, you will see me write it this way. I think it makes more sense. It's easier to comprehend this way. Eventually, we do get lazy and we'll start writing it like this. There's one more. Not gonna lie, don't really use these, but I'm gonna show them to you in case you see them. You're studying with some resources online, and we're like, whoa, what is this? It means the same thing. This one says, we're given some sort of surface. F of x comma y equals, I've got a whole bunch of stuff. 4x to the third y plus 6y squared plus 5x to the third y squared. Our new notation, this is saying take the partial derivative with respect to x. That means you're taking the derivative of the x terms. Anytime you see a y, it's treated as a constant. So we just take it term by term. The derivative of 4x to the third is 12x squared. Constants just come along for the ride. So the y just tags along for the ride. If we're thinking, hey, I thought the derivative of a constant was 0, that's if it's by itself. Like if I'm taking the derivative of 4 sine x, then that constant just comes along for the ride and is 4 cosine x. But if you took the derivative of just 4, that would the next term has no x's in it. This is a constant, so 0. Derivative of 5x to the third is 15x squared. Derivative of negative 20 drops off. I'll give you guys a 30-second head start. See what you can get for partial derivative with respect to y.
Well, you say respect to y. We're using y as the constant.
Y is the variable.
Y as a variable. Okay. That changes things. No, come on.
So if I'm taking the derivative with respect to y, then this is a constant out front. So the derivative of something y is just the something. The derivative of 5y is 5. Well, the derivative of this constant, we're treating x as a constant, is 4x to the third. Derivative of 6y squared is 12y. The derivative of everything else goes up. Questions? What about second derivatives? Yes. This notation, f of xx, or f sub xx, I should say. No, but we'll have another notation in a second where we do something similar.
Basically, when we're taking, like, with respect of, we're ignoring, not ignoring, but like, pretending it isn't,
You're pretending it's no longer a variable, but it's just a constant.
okay, so then you're just, if it has an x for fx, then you're taking the derivative of that.
Yes.
So whatever you're taking respect to, that's your constant.
Variable.
Your variable. Ah, still getting that mixed up in my head. Okay.
So this notation is saying take the partial derivative with respect to x, and then of that, take the partial derivative with respect to x. So that'll be 24x y. Took the derivative of the x piece, the y just tags along to the right. Plus 30. We can of course do f sub y.
So then we know the y.
Second.
So now we know, like, that y is 12.
This is saying your second derivative with respect to y is always 12. No matter what you plug in, you're going to get 12. There is a new one, though, that we never had in Calc 3. No. You can find a quote-unquote mixed partial. This is saying take the partial derivative with respect to x, and for that function, now take the partial with respect to y.
Okay, so it's like the first part that's switched on to the
Yes.
second.
Yep. Now, these feel familiar. This is just like calc 1. You find the second derivative. And yes, it does give you this idea of concavity, increasing and decreasing. This is something we will dive into in a later lesson. So now I'm going to go to my partial derivative with respect to x, but take the derivative, partial derivative with respect to y. Now, go to your partial derivative with respect to y, and take the partial derivative with respect to x. Say again?
It's come out to the same thing, probably.
I'll let you know, that is not. This idea is what we call quote-unquote Clairaut's theorem.
Obviously, basically just take the derivative of the thing that has both x and y. You just take the derivative of the thing that just has both x and y.
So this is saying take the partial with respect to x of that thing, take the partial derivative with respect to y.
So then it's whatever, okay, so then it becomes like partial derivative of x would be the 12x.
So it's just the constant coefficient. Everything else that has an x is now going to go.
It doesn't matter if it has an x and y.
Say again?
I'm just confused because why did you ignore the rest of everything of x?
Because I'm taking the derivative, the partial derivative now with respect to y. Y is the variable. So this is just a constant. There's no y.
Okay, so are you looking at f of x, or are you looking at the original function?
So this one,
Yeah.
I took the partial derivative with respect to x here. Now, you're taking of this one, the partial derivative with respect to y. Now, y is the variable. Everything else is constant.
Oh, so you're looking at, okay, I think so I thought you were looking at that, the original function.
So coming over here, the partial derivative with respect to y, and then partial derivative with respect to x. What I'm showing you here is, it's not a coincidence that they're the same. So, partial derivative with respect to x, then y, means the same thing, saying the partial derivative of y, and then x. We call that Clairaut's theorem. We're going to do another one.
Theorem. It's beautiful. You're right. Indeed.
We'll stick to the same issue. Alright, I'm going to give you a head start here. Take 2 seconds, lean to the person next to you. You have to be careful. I'll let you know this has a whole bunch of changes. It might not look like it, but don't forget, if y is treated as a constant, this is now a chain rule. You could think of this as like e to the 2x.
So, for this one, do x just do cosine? Because there's both x and y, maybe do I still just do cosine?
It's cosine of keeping its essence
Okay.
times.
So as a chain.
Okay, I did it.
Calc 1 says it's going to be cosine of keep the inside the same. Then multiply by the So, if I want the partial derivative with respect to x, Calc 1 says the derivative of sine of something is cosine of something times the derivative of the inside. And we just need to remember now, anything that is not an x is treated as a constant. 6, you can think of this as like plus, but the derivative of y is equal to 0. Plus, what is the partial derivative with respect to x of x squared y to the third?
2x, y, c to the third.
2x y to the third. Another chain rule piece, minus the derivative of e to the anything is e to the anything times
Y.
y. The derivative of xy, don't forget y is a constant, so just
So I'm gonna put that y in the front of like minus y e to that y.
Yep. So you can think of this as like e to the yx, so like e to the 2x, e to the 7x. So times the derivative of that coefficient.
He wanted to put the y up front, doesn't matter, right, since it's.
If you wrote it as minus
Since
y.
it's
Was that your question?
Yeah, that's why I did.
I see
put
it,
the
I see
y
it.
at the front. Right?
Since it's commutative, I mean, yeah.
Doesn't mean anything different. We're gonna get proficient enough that our answers are going to look like this. Partial derivative with respect to x of that, take the derivative with respect to x. Derivative of cosine is negative sine. Keep the inside the same times derivative of the inside. Then I should have the original 6 out. plus, that'll be 2 y to the third. Derivative of e to the anything is e to the anything times the derivative of the anything. And yep, again, you could have written this as a y. And absolutely, you could have written it as a minus y squared.
E to the next guy.
Okay.
Partial derivative with respect to x, grab this one, and now take the derivative with respect to y. That'll be -6 sine of keep the inside the same times what is the derivative of the inside with respect to y? Just a 1. Coefficient here is 1, 6x is a constant. There is no times anything on the inside. That's not what we should say. Say again? The coefficient there is 1. Plus the derivative of 2y to the third is 6y squared. Oh, sorry. I'm looking down.
Yeah.
My bad.
So I did like 3 times 2x y squared.
Yes. So that'll be 6x And what are we thinking for the last term? Well, y is my variable, and you agree that these two things are being multiplied, right?
Mm-hmm.
Which means what? The product. So I've got derivative of the first, keep the second, plus keep the first times derivative of the second. I'm going to underline that in a different color just so we keep it.
Yep.
So one more time, derivative of the first, derivative of negative y is -1. Keep the second, plus keep the first, derivative of the second. Now we're going to do very similarly f sub y, f sub yy, f sub y. Cosine of keep the inside the same times the derivative of the inside is just 1 with respect to y. Plus 3x squared y squared minus. Now, if I have e to the xy, then yeah, the x is kind of the coefficient now. So that's going to be the piece that gets dropped there. F sub yy, that's going to be negative sine 6x plus y times derivative of the inside is still just times 1. Plus 6x squared y. Minus x times the derivative of e to the xy is e to the xy times x. Then lastly, the derivative of y and then x. That'll be negative sine 6x plus y times 6 y and x. We got derivative of the first, so minus 1, keep the second, and then keep the first, derivative of the second. And this is y, then x. It's going to be y, right? E to the xy? I'm taking the derivative with respect to x, and y is my coefficient.
Would you want two minus signs? Because it's minus.
Are you saying, so careful, we're not going from here to here. We're going from here, and then taking the derivative with respect
Oh,
to
no, I
x.
mean, with the e, would you have minus negative 1 times e to xy?
Here?
Yeah, because the first derivative is negative 1.
So derivative of the first, keep the second, keep the first. The derivative of this with respect to x will be y. E to the xy.
Yeah.
Yeah.
But also,
That's the one.
So we're gonna change that one then to x, so negative y times x into the xy?
Derivative of the first, keep the second, keep the first.
Derivative
Derivative of the
second.
second, this is with respect to y, so this should get x. We were gonna get there, I promise, but hang on. How did I know that I messed up? There would have been a way that I know that I did something wrong somewhere.
The two won't be the same.
Right. Clairaut's theorem says that these mixed partials should be the same.
Right.
So I've got negative 6 sine of 6x plus y. I do have a negative 6 sine of 6x plus y. 6xy squared, check. Minus e to the xy, check. Minus x times y, e to the xy, x times y, e to the xy. Cool. Questions? Alright, we're going to do one more. We're just going to change up the notation, because it is going to be slightly different if we use the other one. top one, partial derivative with respect to x. We recognize this is kind of looking like the same thing, but please note a huge star on your paper. In this notation, unfortunately, we have to read it a little bit differently. Over here, we read left to right. This is saying take the partial derivative with respect to x and then the partial derivative with respect to y. Over here, this is saying we have to read this right to left. Partial derivative with respect to x, and then the partial derivative with respect to y. It's the only thing different about this notation. It's just right to left. practice problems practice problems, it's really just compute the partial, flipping it over, maybe puts it in words, find the slope of the tangent line. But it's really just exercising, can we take partial derivatives? When we come in Friday, we're going to start looking at what can we actually do with these partial derivatives. Any questions? Bye everyone, I'll see you Friday.
All right now. Yay.